Okay, it's time for me to start working on this here pulse width modulation motor control now for my mini lathe. And the first thing I need to do is I need to take this off the wall, the whole thing here, and I need to disconnect all the wiring, get all the circuit boards off here, and get it back down to the linear power supply. And then from there I can start designing the circuit for the pulse width modulation new motor control circuit now. This time when I build this new circuit, I'm not going to use any printed circuit boards. I'm going to do it all on breadboarding here. That'll make it easier to work with and also make it easier to change out components if I should need to. There's my circuit diagram there I'm going to be going with. When I start designing the circuit, I'm going to explain every detail of how I'm designing the circuit. I'm going to do one step at a time and do measurements and do tests and things like that, and we're going to do it all from scratch. There we go. Power coming in, motor wires going out. These are all these circuit wires here going to the fan, going to the circuit board, and all these wires got to come off. Everything's got to come off that's going to the outside here. Yeah, got all the wires off here. Box just come right up now. Careful there, buddy. Oh, there we go. One more wire. Alrighty. That's all of them. Okay, I'm back on my bench here now. Get everything here taken off now and get it down to the linear power supply. Okay, there's a circuit disconnected from the board there, from the box. I'm down now to the linear power supplies, capacitor bank, transformers, and my bridge rectifiers. This bridge rectifier here is for running a DC fan, and this bridge rectifier here will be running the complete circuit for the circuit board. And then I'll have to also get the 80 volt. This comes about 80 volts, these two here, down here somewhere, and that will run the motor itself. Okay, first I'm going to do now is I'm going to hook up the wires now here to the main supply and turn the supply on and just make sure the fan's running okay, and check some voltages here and get myself some idea here of what voltages I'm going to be working with here on DC. Go ahead and plug this in here now. Fan is running good. Okay, so I know that everything's working good there. Now there is one thing that you want to do. Anytime you have a linear power supply, you're always going to have the peak voltage of the DC coming out of here is going to be across the capacitor. So I got a plastic handle here and a 5 ohm 5 watt resistor, and you always want to discharge the capacitor bank always. By discharging like that there, and now I bring it back to 0 volts again. Okay, so I know now that the supply works good, the fan is working good, so now I can check some voltages here and start designing the circuit for it now. Okay, the first thing I did was rewire the whole linear supply, because the last circuit I had on here, I used all of the motor voltage and the circuit voltage on the same power supply. But on this new circuit I'm building, I need to have two separate supplies. I need to have the full 80 volts for the motor itself to run, full 80 volts, and then I have a small transformer here with another bridge rectifier and a bank of capacitors that I'm going to use for the logic circuitry now. I had to cut the leads here on the bank of capacitors, so I have 5 for the motor and 5 for the logic circuitry, and that way there I can still use the same capacitors. So that's what I did this evening, was get all this here ready to go. So now I have 20 volts for here and 80 volts here, and that's what I'm going to need to use now for this new setup. I have a breadboard set up here now ready to go, and then we'll start designing the circuit and start building the circuit now. Okay, the first circuit to build now would be the Schmidt trigger circuit, and that's being used as a level detection circuit. And it looks like this. We have our 18 volts power supply. This will be our input transistor. And we have our output transistor. And then we have our output resistance, or this is our pull-up resistance, and then the output itself. Designations are as such. This is RC2, RC1, RB1, RB2, RE. This is transistor Q2, and this is transistor Q1, and this is the input. Okay, now I have a design formula that I came up with that I can use to get these here values here, and that's what's going to come up next here now. Okay, now going into the base here, I want to use a variable resistor. I have what I have available right now is a 5K ohm resistor. I want to put a resistor of 1K up here to the positive side of the battery, and another 1K ohm resistor here down to ground. And the reason that is because this resistor here is going to eventually be replaced with an active component. But I want to put a 1K ohm resistor here because I want to use this as a security resistor, so that if I take my potentiometer up too far up on the scale here, I'm not going to burn out the transistor base here, because I'll still have 1K ohms in series with the base input here. Like I said, I have a 5K ohm resistor here for my potentiometer. That's what I have available, so that's what I'm going to use. And the first thing I want to do is, before I even design this part of the circuit here, I want to get the threshold voltage that I want to use to trigger the circuit. And in order to do that is I'm going to build this part right here only, and I'm going to find out when I put my potentiometer at a certain point on the scale what the voltage is here, and then I'm going to use that to determine the input voltage for the threshold voltage for it to trigger on. I have set up right now is just the voltage divider itself right here, a 1K ohm resistor, a 1K ohm resistor, and a 5K. Just that part right there I have set up. I have it right here. I have a knob on here also because I want to give myself a visual of how far the knob goes for me to set my voltage. So what I want to do first of all is I want to set this to the extreme left here, and that's going to be the negative side, and I'm going to take a voltage reading of what that comes out to. Plug this in here. Okay, so I'm to the extreme left right now. I'm going to record that voltage. I'm at 2.7 volts. So I'm going to record that voltage for 2.7 volts extreme left. Now I'm going to take it to the positive side. So I'm going to take it to extreme right now until it stops. And the voltage comes out to about 15.8. Okay. Now with that in mind, I'm going to set this to where I want the knob at here. Now I want to set the knob, say, about right to here. When I get to about right here, I want this to start triggering the circuit. So if I look at that voltage, I'm at about 3 volts. So when I bring this back to here again, I'm at 2.7 volts. When I increase that to about 3 volts, I'm going to give it an extra here, about 4 volts, 4.5. I'm going to go about 5 volts. I'm going to put the knob in that direction here. So I'm going to use 5 volts. 5 volts is going to be my threshold voltage, upper threshold voltage. What that means is when I raise this to 5 volts on the base here, this circuit's going to trigger and go high on the output. Okay, now that 5 volts that I was talking about, that's pretty close to that 2.7 volts on the negative side of that. That's not going to be good because I'm going to be driving that very quickly into that region there. When I get to around 2.7, it's going to be triggering. So what I want to do is I'm going to remember I have a input signal coming in here also, a sine wave coming in here too. That's going to be working this. So right now what I'm trying to do is establish the base voltage for the trigger point. So I think I better increase that to maybe 9 to 12 volts maybe, and that would give me enough headroom to work with on this 18 volt supply. It also allows it to drop down lower as need be to get it to a slower speed too. So I'm going to go at 12 volts for the input. 12 volts will be my upper voltage, threshold voltage, so I'll call that VU. VU equals 12 volts. Okay, after looking at a lot of different Schmitt trigger circuits and studied them and everything, I came up with my own set of equations here that helps me to design my Schmitt trigger circuits. And what it is I have a value that I can choose for VCC. I have a value that I can choose for the upper threshold voltage. What I do is I don't use a lower threshold voltage as it's usually done when designing Schmitt trigger circuits. I just need the one threshold voltage only, and that's the upper threshold voltage I go by. I'm not concerned about hysteresis or anything like that. I'm just interested in just getting the trigger at a certain point for a threshold. Then I have for RC2, that is the output resistance here. I use that as a chosen value also. And then for VE, that's the emitter voltage here. That is the upper voltage or the upper threshold voltage minus the base emitter voltage of Q2. And then I'll just keep on going along here as I'm working out the circuit here. I'll just go one step at a time here. We'll do this one step at a time. Okay, so right now I know that I want VCC to be 18 volts, so I'll put that here for 18 volts for VCC. I know that my threshold voltage, the trigger voltage, I want that to be 12 volts. I came up with that before. Now for RC2, that's this output resistance here. I'm going to use, since I have a lot of 470 ohm resistors, I'm just going to use a 470 ohm resistor for that. And that'll be my resistance right here, RC2. And now I'll start solving for these other equations here. For the emitter voltage, that is the threshold voltage minus the base emitter voltage of Q2, which would be around 0.7 volts. So only 12 minus 0.7 or 11.3 volts. 11.3 volts for the emitter voltage. RE, okay, now the emitter resistor right here, that is RC2, which is given here now at 470 ohms. We're going to take that times the emitter voltage of 11.3 volts, and then we're going to divide that quantity by another quantity, and that is the supply voltage VCC minus the emitter voltage. And I'll get that calculated. It comes out to 885 ohms, so I'm going to make that 910 ohms since that's the resistances that I have. That's close enough to that. Now RB2 is 10 times that RE value, so that'd be 9.1K. And now I'm going to solve for IB2. IB2 is the current that's going to be flowing from the supply voltage down through RC1, RB1, and down through RB2. That's going to be the current that we're solving for here. So to get that current, we're going to take the VU, which is the threshold voltage again of 12 volts, and divide that by the value of RB2 that we just figured out right here of 9.1K. That's about 1.31 milliamps. Now we can solve for RC1 right here. And I found out that it works good to make that about 0.1 volts dropped across there. So for RC1, if I take 0.1 volts and I divide that by that IB2 value that we just solved for, and that would give me RC1. 763, so I'll make that 750 ohms. And that'll be RC1 value. There's only one resistor left over here now, and that's the collector to base from Q1 to Q2 right here. And that is solved by taking supply voltage, subtracting that 0.1 volts dropped across RC1, and then subtracting the threshold voltage, the trigger voltage of 12 volts, and then dividing that by the IB2 value that we solved for up here, 1.31 milliamps. And we'll get that now. It's about 4,500 ohms, and that would be about 4.7K or 4.3K. So I'll put 4.7K for starters. We'll try that, see how that works. Okay, let's put these values now in the schematic here. RC2 is chosen to be 470 ohms. RC1 is 750 ohms here. RB2, and that would be 9.1K. RE is 1/10 that, which is 910 ohms. And then we have RB1 here, and that is 4.7K or 4.2K. We can go either way with that, and we'll see which one works better. Alright, let's go ahead and build this and see what we get here on a trigger voltage. Okay, I had to change RB1 from 4.7K. I had to change that to 4.3K because 4.3K gets it closer to 4.5K than 4.7K was. It's better to have this more lower than higher so that this here would trigger a lot quicker. Or I should say, it'll trigger too quick if I have it too high. But if I lower this a little bit to 4.3K, then the triggering will be more in line where it needs to be. Okay, so let's look at the, here's the input voltage here coming up. And I have my oscilloscope set up here. I'm going to show what it looks like once the input comes to the threshold voltage. What happens is it was going to snap up real quick, like that, and snap back down. Alright. Now here's the input voltage right here coming into it. I'm at 11 volts right there, and I'm still down on the screen there. As I increase the voltage a little more here now, right there, I'm up to the high point now. And of course this is going to drop because there's a change in resistance now, that because it switches over, there's a change in the voltage input to the base now because of that. But it is triggering like we want it to do. The lower threshold voltage is about 8 volts, and then drops back down. Okay, so the Schmidt trigger is working. It's working properly. What I'm going to do now is I'm going to hook up my audio signal generator to the circuit, and then we're going to watch how that works on the oscilloscope now. Now I have it hooked up to my signal generator, and I have it hooked up to my oscilloscope. I'll just turn the knob here a little bit, and we'll watch what happens on the screen here now. Now we're getting a square wave, and we keep on turning the knob, and we get full DC. So we know that it's working. Okay, so that verifies then that it is working for a Schmidt trigger circuit. So the next thing now will be to start working on the rest of the circuit now. The bottom waveform here is the sine wave. That's the input waveform, and this is the output waveform right here. So again, as I adjust the potentiometer, the input waveform begins to rise above the ground until it gets to a point there where it triggers it on, and then we just keep on increasing the potentiometer, which causes this waveform to go up higher into the threshold region until finally we get pure DC output here. And then we bring it back down to 0, back up again, full, back to 0 again. Okay. Okay, so now we still cannot run our motor yet, because when this here circuit is not triggered, there is still a idle voltage here, and that voltage is a little bit higher than the threshold voltage we're looking for. What we're going to do is we're going to take a voltmeter reading right here at the output here when there's no triggering signal coming in whatsoever. So what I'm going to do is I'm going to touch the output here with my voltmeter right here, and under no signal condition we have about 12 3/4 volts. So we'll record that. We have 12.75 volts, roughly we'll call it. So 12 3/4 volts standing voltage. So now if we were to apply this to the motor right now, it would turn the motor on, and we can't have that right now until we get a valid input signal. So what we need to do now is we need to make a transistor stage here that's going to be a comparator. And what that's going to do is that's going to compare a voltage at its emitter to this standing voltage here, and when this voltage rises during an input signal, then that transistor will start to conduct them. So let me go ahead and get this here drawn up now. This comparator stage, we'll use an NPN transistor like this. We'll take its collector directly up to the positive side of the battery, but we need to put a resistor there. we'll put a resistor there so that we can develop a voltage across there, because we've got to send the signal through the collector to the next stage. Now we can go ahead and connect this here base up to the output of the Schmidt trigger circuit, the threshold circuit, at 12.75 volts. Now we'll put a resistor there, of course, feeding into there too, and that's where I'll just come up with a resistor value for that. Now here's where the comparator signal works at. At the emitter here, we're going to make a voltage divider, a resistor to the positive side of the battery and a resistor to ground. The resistor to ground is going to be the current, is going to supply the electron current for the next stage. The resistor here is the pull-up resistor, and this forms a voltage divider. Now we want to do is, I have a lot of 10k ohm resistors, so I'm going to use a 10k ohm resistor here for the emitter resistor here. Now I'm going to solve for this resistor value here, and then what I'm going to do is I want to put about 12.75 volts at the emitter that matches the 12.75 at the base, so that this here transistor will not conduct under idle conditions here, where the Schmidt trigger circuit is not operating, where it's in idle mode. There will be a 0 voltage across the base emitter here, roughly in that area there, roughly in the cutoff, and that way there then we can have a valid input signal come in. Then this transistor will start conducting. So let me get this here value here for this here resistor here now. So for this here resistor value up here on this here voltage divider here, since I have 12.75 volts that I want to drop across this 10k ohm resistor here, I'll take 12.75 and I'll divide that by the 10k ohm resistor, and that gives me about 1.27 milliamps current flow through here, ground. Okay, take 1 over that times, now I'm going to take this current and I'm going to divide that into the difference between the 18 volt supply voltage minus the 12.75. 18 minus 12.75, and that'll give me about 4.1k, so I'm going to go with 3.9k since that's the closest one I have available there. And we'll see what that voltage is here. If this is that should make that a little bit higher, so that should definitely keep this in cutoff here. For this resistor here, I'm going to just choose another 10k ohm resistor here at the collector, because I have, like I said, I have a lot of 10ks. And I think I'll just put a 10k right here for the base input resistor as well. And if it's not working properly, then I can make changes here, and I'll explain how I make the changes if there's a need to make any changes. Okay, so what I'm going to do now is get this here part built here now, and we'll give that a test out. Here's stage built here, the comparator stage. And we'll take a voltage reading here at the emitter here, which is that divider here, and we want to be at least 12.75. Okay, we're about 13 volts. So we are higher here at the emitter than we are at the base of the NPN transistor, which means is that this transistor is in cutoff. So what we're going to do now is we're going to put our oscilloscope on the output here, on the collector here, and we're going to check and see if we're getting any kind of waveform, make sure that we're getting our square wave output with a sine wave input. And of course this time it's going to be an inverted wave, because this is inverted stage here. And let's see how that looks now. But here's our input coming in, here's our output. Our output is showing high here because remember, we're on an inverter stage. So right now I'm hitting 18 volts on the output of this stage because it's inverted. Now as I begin to give an input again, we begin to get, it begins to drop down as we see here. So we got our square wave again, and now we're down here, which means is that the stage is operating, which means is that we're actually pure DC, because remember this is an inverter stage. Okay, so now we want to take this inverted output here, which is and we want to take that into a PNP transistor now, so that we can invert that back the right way and have a square wave that goes up positive. And then that's the stage that's going to drive the motor itself. So now we're ready for the next stage, and that's going to be a PNP stage, so that we can take the positive output here, the negative output here, electron current flow, and we want to take that into a PNP transistor here so that we can invert that back to a positive output flow. Now, for the base resistance here, to relay the signal here, I'm going to go with a 100k ohm resistor, and the reason why is because we have a previous stage of amplification here. As we keep on going down the line here, we're getting more and more amplification, so we have to get smaller currents into the base, or else it's going to overdrive the base. So I'm going to put a 100k ohm resistor in the base here. That's going to be used for the signal. Now, the emitter, I'm just going to take that directly to the positive side of the battery, because this is going to drive the gate. This is going to be the gate driver for the MOSFET. The output of this PNP transistor is going to go to a resistance of some value here, and this is going to form another voltage divider here that's going to go to the gate of a MOSFET. So I'm going to choose a value of, let's say, 10k here again, because I've got plenty of those resistors, and I'm going to choose a value of 10k here. Let me get back with this on this. I want to drive this MOSFET into saturation, or into heavy conduction. I'm going to just go directly from the collector of the PNP directly into the gate. Now I have to have a gate resistor here around 10k. I'll probably change that too. We'll see how that works with this here. But I have to have that there in order to bring the resistance, or bring the gate voltage to shut the MOSFET off when this is not conducting. Okay, now the bottom MOSFET here, which would be the source, that will go to ground. I may change this value here, so maybe I'll start out with 1k instead, to the gate from ground, to ensure that this here gate is being turned off. Now, the MOSFET's going to drive the motor, so I'm going to drive the motor directly off of the MOSFET drain, and I'm going to put a diode across there for kickback, and then I'm going to put in a resistor of 0.22 ohms, which will become the sense resistor. With this setup right here, we should be able to at least get the motor running under pulse width modulation and see how that works. So let's get this here part built now. Okay, this here PNP stage is now built here. I don't have the motor hooked up yet. And all I want to do is check and see, right here it is, I just want to check and see if the waveform is functioning properly, and we're inverted back to normal again. So now we have our pure DC on top there, and so we're back to normal on the inversion now, so we got everything back to normal that way. So now it's a matter of hooking the output of this PNP transistor now to a MOSFET, and hooking the MOSFET to the motor, and see how we have any kind of pulse width modulation with the motor load now. And that's coming up next. Okay, I now have the motor hooked up here to the 80 volt supply, and we have all this here circuitry completely done here, and it's all built right here now. And here's the waveform. And now we'll go look at the motor itself. Alrighty. So we have the motor running now. Now, since I don't have no feedback yet, it's going to stall. But I can hear I can feel the pulses in there. So we'll go ahead and turn this on here a little quicker now, and we'll take a look at the speed of the motor. Okay, so the pulse width modulation is working for running the motor. The next part of the circuitry now will be to design the torque feedback circuitry now. That's coming up next.